So we left off on Wednesday discussing the cardiac cycle. So we have as our warm up for today just a couple questions about the phases, those named phases of the cardiac cycle. What's happening there with the pressure, which we could also relate to the change in volume. We're going to be picking up with that today. So hopefully your answers look something like this. Ooh. Looks like the bottom here is cut off. But talk about it. Okay. So during the cardiac cycle, we have two phases where we see the ventricular pressure changing, but not the ventricular volume. So those are isovolumetric ventricular contraction and isometric ventricular relaxation phases, which are numbered 2 and 4. Causing this change in pressure, what we have happening is that the ventricle is either contracting, phase 2, or relaxing in phase 4, while all the valves are shut. So we don't see a change in the volume of blood in the ventricles. We keep that same amount of blood. None of it escapes because our valves are closed. But because the walls of the ventricle are either compressing or expanding around that blood, we do see changes in pressure. These changes in pressure will eventually result in a change in the state of the valves. So these phases are both relatively brief, because once the pressure reaches a peak, or once it gets high enough during isovolumetric ventricular contraction, that opens the semilunar valves, that high pressure starts to escape into the arteries leaving the heart. Similarly, in the opposite case, while the ventricles are relaxing, once that pressure gets really low and the atrial pressure is higher, that opens the atrioventricular valves, starting over our cardiac cycle, basically, starting us through these phases again. Okay. So we can see that in this image. So we looked at diastole, which is relaxation, and systole, which is heart contraction. And we related that to these phases that name what's going on with the ventricles. First, we fill the ventricles with blood. At the end of this phase, the atria contract, pushing the rest of the blood into those ventricles. Then, systole, our ventricles start to contract. At first, they do this with the valves closed. Then they overcome the necessary pressure to open the semilunar valves, and we enter ventricular ejection. Blood starts to leave those ventricles through the arteries, so through the pulmonary trunk and through the aorta. And then eventually our ventricles start to relax. As they relax, blood would want to backflow, but it can't. So those semilunar valves shut from this change in pressure. And we have isovolumetric relaxation. So we have our valves shut, but the heart muscle is relaxing. When we're fully relaxed, the atria start to fill again, leading us into ventricular filling, and this process starts over. So when we left off on Wednesday, we were comparing the pressure in the atria and the ventricles that guide some of this process. So we saw that during phase 1, while we have those AV valves open, we see that the ventricular pressure is slightly lower than the atrial pressure, and our blood flows from high pressure to low pressure. So this is why we see blood flowing into the ventricles. During phase 2, we see that the ventricular pressure shoots up. All those valves are closed. So because they're closed, we don't have backflow of blood into the atria, even though that pressure is going down a bit. During phase 3, we see that we reach our peak of ventricular pressure. It's because we're still contracting as we eject blood. But eventually we don't have that much blood to push on. So because volume of blood is escaping the ventricle, so the pressure starts to go down. Once it goes down enough, this slams shut our semilunar valves. So ventricular pressure continues to drop. And then we start over again. So today we're going to be talking about the relationship in pressure between those ventricles and the aorta, which is our artery leaving the left ventricle. So one of the main arteries that we're concerned with, leading into our systemic circuit. To remember, the left side of the heart going to the systemic circuit, the right side of the heart is our pulmonary circuit, so just getting that blood to the lungs to be oxygenated. So we're going to look at what's going on in the pressure in the aorta and how this relates to this big picture of what's going on with the heart. Okay. So this is what we did last time, comparison of ventricular pressure and atrial pressure. So now we want to think about the aorta. So pressure in the aorta is going to be important because we're basically going to be using the walls of the aorta as a pressure reservoir in order to maintain pressure through the systemic circuit during diastole, so while the heart is not pushing blood out. So we actually very often are concerned with aortic pressure. So during diastole, our aortic valve closes. So as the heart relaxes, we don't want blood flowing back into the heart from the arteries. That's nice oxygenated blood in the aorta. We want it to go out to the body. So the aortic valve, which is one of our two semilunar valves, closes. Blood is still leaving the aorta during diastole, so we're continuously pumping blood out to the body. So blood leaves the aorta so that pressure starts to fall in the aorta. So right before this, we pushed all our blood from the ventricle into the aorta. So that's where the pressure was at the beginning of this. So here we see our aortic pressure falling as blood is flowing from the aorta out to the abdomen, down to your legs, wherever it's going. Okay. So pressure is falling. The lowest point of pressure here is what we call our diastolic pressure. So when we're measuring blood pressure, we measure diastolic pressure and we measure systolic pressure. That's why we have two numbers, right? So the diastolic pressure, that lower number, is telling us the pressure in the aorta at the dip here during diastole. So that's our diastolic pressure. During systole, as the heart contracts, right, for a little bit in phase 2, the ventricles are contracting, but no blood is coming out. But then once the pressure in the ventricles gets high enough, that aortic valve opens. So that semilunar valve opens. And we're rapidly pushing blood, all the blood in the ventricle that we can, into the aorta. This means that the pressure in the aorta rises rapidly. So it's rising rapidly where the blood is going, right? And this highest point here, so the highest point of pressure in the aorta during that ventricular ejection phase when the blood is moving from the ventricles to the aorta, that's our systolic pressure. So if they tell you your blood pressure is like 120/80 or something, that's telling you this peak during systole versus this dip in diastole. So if we're looking at this graph, what we actually see, right, is a blood pressure 110/70. So that's our systolic pressure versus our diastolic pressure. Okay. The aortic valves do close. So as they close, we have a slight backflow of blood into the aorta because we had low pressure building up, and we have low pressure being created in the ventricles because they've pushed out all their blood and now they're relaxing. So the blood tries to flow backwards, which means it builds up in the aorta for a second here, causing a slight notch before it then starts to fall again, right? So that's just a brief backflow before it starts going the right direction. We'll talk about what's causing that blood to continue leaving the aorta in a minute. A number that you'll see a lot as we move into ANP2 is this value MAP. So that's our mean arterial pressure. So this is going to be basically an average of pressure in the aorta through this whole cycle. So you'll note it's a little closer to the diastolic pressure than to the systolic pressure. And that's because diastole lasts a little longer. Okay. Here we go, in words. So our mean arterial pressure is the average pressure in the aorta occurring during the whole cardiac cycle. Now, this is important because the pressure in the aorta is what continues moving blood through the systemic circuit. So out to your liver, out to your gut, out to your, I don't know what, your pancreas, everywhere that gets blood. So everywhere in the systemic circuit is getting it because we keep this mean arterial pressure relatively high in the aorta, right? We're pushing blood out to the system. We have continuous blood flow during the cardiac cycle. It's very important that we don't have blood just like stopping and chilling out in your body. Right? We want to keep blood moving because we want it to get out to the tissue. Then we want to send it back to the heart to replenish the oxygen. So the way we do this, the way we keep sufficient pressure in the aorta, so that the aorta and other large arteries are elastic, which acts as a pressure reservoir, right? So you can basically think about it like with my balloon, right? So blowing up my balloon, right? So I've put pressure, my balloon, my aorta right now. What's actually happening is that the elasticity of the balloon, so this like stretchiness, is actually holding pressure. So as I release the, whatever this is, the neck of the balloon, right? Air is going to continue to flow out of the balloon because as we decrease the amount of volume in this balloon or in the aorta, we have this recoil. So this maintains pressure on that lower volume of blood. This is basically energy being stored in the walls of the aorta during systole. So they expand, storing pressure in that elasticity. And then it gets released during diastole as the walls contract inward. Okay, so that's the aorta recoiling to allow that blood to flow. Okay. So the aortic pressure is maintaining the blood flow through the whole cardiac cycle. So we're storing more pressure in that elasticity in those walls during systole, and then we're using that elasticity, that stored energy, to produce pressure during diastole. So we can take a look at what this looks like as well. Okay, so here we see what's happening during systole. So because we're talking about the aorta, we're talking about blood from the left ventricle here. So we can see it flowing into the aorta. It's pushing, it's high pressure blood, it's pushing open that aortic valve, right? And it's high pressure. We're pushing more and more volume into the aorta here. So these walls are expanding as we push blood into it. Right, so expanding the pressure due to the increased volume. Then during diastole, our left ventricle becomes a low pressure system. So blood would want to backflow, but as it backflows, it catches on the edge of the aortic valve, which shuts the aortic valve. So blood cannot move back towards the left ventricle. That means that the blood has to go the other direction. So it's flowing the other direction, but we know that blood only flows from high pressure to low pressure, right? Like that's how we get movement. And the reason we're maintaining the pressure in the aorta higher than elsewhere in the body is that this elastic recoil is pushing down on that blood even as it flows out. So this is the aorta acting as a pressure reservoir in order to maintain blood flow through the systemic circuit. So these arrows are showing us where the pressure is going. So here it's being stored in the walls, and here it's recoiling back. So we call this elastic recoil. I think I have a poll question set up for this one. Okay, I'm going to go ahead and end the polling. Okay, so it looks like there's a little confusion here about exactly what systole and diastole means. So the most chosen answer is correct. The heart does spend more time in diastole, so A is correct. But just to reiterate, so systole and diastole refer to whether the ventricles are relaxed or contracted. So systole and diastole are specifically defined by the state of those ventricles. But if we say the heart is in systole, like the whole heart is referred to as in systole. So we can't have the atria in a different amount of time in systole because we refer to the whole heart as being in systole, even though we define it by the state of those ventricles. Okay, so yeah, diastole is a little longer than systole. The heart is relaxed more than it's contracted. Okay. So thus far, we've been talking about pressure. And we've talked about volume a little bit, but there are a couple specific volumes, specific named volumes that we want to think about now. So we've just been talking about how much blood is in the ventricles at any given point and how that relates to pressure so far. But we're also really interested in how much oxygenated blood is getting out to the body during any given heartbeat. So we're going to want to be able to calculate basically how much blood we're sending out to the body during our cardiac cycle. So your ventricles are not perfect. They don't actually manage to squeeze all the blood out of them every heartbeat. There's always a bunch of blood kind of left in the heart. So we're going to refer to two values of that blood that's kind of left. So we have our end diastolic volume. This is the volume of blood in the ventricle at the end of diastole. So at the end of diastole, we have our end diastolic volume. Now remember, diastole is our relaxed ventricle, right? So part of diastole, we had our valves closed, but at the end of diastole, that also includes phase 1 of our cardiac cycle, the ventricular filling. So our end diastolic volume is really going to be the total amount of blood we get into the ventricle. So the end diastolic volume, we can think of kind of as our heart being full. Our end systolic volume, right? Systole, ventricles contract. The end systolic volume is the amount of blood that's left in the ventricle at the end of systole. So it's like the little bit of toothpaste left in the tube at the end, or a little bit of ketchup left in the bottle, the part that the heart can't get out. And it's actually a pretty significant number, I will say. So using these two numbers, the ventricle when it's full, that end diastolic volume, versus the amount of blood left at the end of systole, the end systolic volume, we can figure out how much blood was actually ejected, how much blood was sent out to the systemic circuit. So we refer to that amount of blood that was sent out to the systemic circuit as our stroke volume. So the stroke here being a single heartbeat, right? It's the volume of blood that a stroke of the heart, just like a heartbeat, is sending out to the body. So our stroke volume, if we put this in mathematical terms, is going to be equivalent to our end diastolic volume. So that amount of blood at the end of the ventricular filling, at the end of diastole, minus our end systolic volume, which is the amount of kind of leftover blood after we contract the ventricles. So if we had an end diastolic volume at the end of diastole, so at the end of our ventricular filling of 130 milliliters, and then at the end of systole, so after we do our ventricular ejection, we're left with 60 milliliters of blood still in the ventricles. Subtract that, and then we would know that we sent 70 milliliters of blood out into the aorta, which then sent it out to the rest of the body. We are also going to be interested in the ejection fraction. So the ejection fraction is basically kind of like a percentage or a ratio. It's telling us how much of the blood that was in the heart got sent out to the body. So we're comparing that amount. And this is helpful because so you can think if we're looking just at the stroke volume, right? We can think how maybe the size of the heart might matter here, right? These numbers would be smaller. Maybe we don't know exactly what 70 milliliters versus 50 milliliters would mean for an individual because people are different sizes, hearts are different sizes. It might not tell us what we want to know. But if we look at the ejection fraction, it tells us what percentage of the blood in that heart was getting out to the body. So this can sometimes be a more useful number depending what exactly our question is. So the ejection fraction is the stroke volume. So that's the blood we ejected from the ventricles during a heartbeat, divided by the end diastolic volume, which is the amount of the blood in the heart at the end of diastole, but we can think of it as like the amount of blood in the ventricles when they're quote unquote full. So we could end up with the same numbers before, right? For our stroke volume, end diastolic minus end systolic was 130 minus 60, equivalent to 70, right? We can then take these same numbers, 70 milliliters our stroke volume divided by 130, our end diastolic volume, so like our total blood when the heart is relaxed, give us 0.54, so 54% of the blood in this resting state is getting sent out to the body in any one heartbeat, right? So 54% of the blood is getting sent out. So we can see a pretty significant amount is not. Okay. We will see that these numbers change. So the stroke volume, as well as the ejection fraction, depending on how hard the heart is working, right? So we're going to see this change, for example, when you're out on a run. So here we are looking at the volume of blood. So we're looking at the volume of blood in the ventricles during each of these phases. So during phase one, that's our ventricular filling, right? So for a while we have ventricular filling happen passively. Then we see our atria contract, still phase one. We have some more blood being squeezed in from the atria, what was left in the atria there. Then during phase 2, we have our isovolumetric ventricular contraction. We see no change in volume here because that's the definition of that phase. So diastole ended actually at the end of phase 1, right? So right before the ventricles start to contract. So here we can see our end diastolic volume is this peak. So we could measure at the end of phase 1, but if we measure during phase 2, that's fine too, because we didn't have a change in volume yet. Okay. So then in systole, right, we started contracting in phase 2, but now we're doing ejection, ventricular ejection during phase 3. So blood is leaving the heart. So blood is leaving the heart, which means the volume of blood in those ventricles swooping down, right? The amount of blood that leaves our heart is our stroke volume. So if we measured from this peak to this trough, that would give us the stroke volume. Then we could also look at how much blood is left in the heart at the end of systole. So we'd have our end systolic volume, this blood that didn't get out. Okay. And then we would start refilling the heart. So we see it go up until we start the cycle over again, right? We can see that this filling is happening during phase 1. So we can tie this all together, right? So we looked here at the pressure differences, which tell us something about why the blood is moving in a particular direction, because it wants to flow from high to low, so long as the valves will allow it. We looked at how this is related to the valves, both the AV valves between the atria and the ventricles, and the aortic and pulmonary valves, which are between our arteries and our ventricles. We looked at the phases, and here we can see our ventricular volume. So we'll note that the heart sounds are occurring here, basically in phases 2 and 4. So if we think about those heart sounds, oh, we're not onto heart sounds yet. The heart sounds are going to be related to basically the turbulence caused in the blood when the valves shut. But we'll get back to that in a second because we have a pressure volume curve to go over first. Okay, so we can draw a pressure volume curve relating the volume of blood in the ventricle to the pressure caused by the blood in that ventricle. Yeah. So we'll see that during phase 1, right, what this is showing us, this line is moving to the right. So we have the ventricles filling. So we are increasing ventricular volume. This doesn't cause very much of a change in pressure because it's just kind of, I'm not going to say leaking, but it's a kind of gentle flow into there. This isn't a very high pressure thing. There's a pretty small pressure increment during the filling. Next, we have phase 2. We don't change the volume because phase 2 is isovolumetric ventricular contraction. So what we have happening is we keep the same amount of volume in our ventricle, but the pressure shoots up because we contract the walls around that blood. So the ventricles are contracting. So we see a dramatic upshoot in the pressure of the left ventricle. During phase 3, which is ventricular ejection, we start to see blood leaving the ventricles. So we can see that this arrow is moving to the left. So that's the left part. Our x-axis is the volume. The pressure is rising because we're still in systole. So the ventricle is still contracting. So we will see that during phase 3, we still have some increase here in the pressure on that blood. We can see that it does start to drop off, and then it enters phase 4. Right, so during phase 4, we see a straight down line because during phase 4, that's our isovolumetric ventricular relaxation. So whatever volume of blood is left in the ventricles, that's how much there is. So here we have 60 milliliters. Nothing's coming or going because our valves are shut. but the ventricle is relaxing, so that space is getting kind of bigger. It's putting less pressure on that volume of blood that remains. So this is our pressure volume curve, and it tells us what's going on with the amount of blood in the heart and the pressure in the ventricles. So this summarizes, there are two really important pieces of information we might want to know. How much pressure, so how much force is being exerted on that blood, and also how much blood there is. So those can both tell us important things about the functioning of the heart. Now we have our heart sounds. So heart sounds are due to turbulent flow when the valves close. So turbulent, right, means kind of like a wave crashing, right? A wave, when it crashes, it makes noise because that water is getting jostled around. That's what the heart sounds are. It's the jostling of the blood. So this turbulent flow is caused when the valves close. So you think about the valves close, and then the blood itself shakes around as that door gets closed, and that blood sloshing around causes the sound. I'm emphasizing this because people kind of get this confused fairly regularly. It's not the sound of the valves themselves. When we're listening to normal heart sounds, it's the blood flow. So when we're listening to our heart sounds, we're going to see two heart sounds. First, we're going to hear a soft lub. This is the sound of the turbulent flow after the AV valves close. So the AV valves close simultaneously. We have some backshift of blood towards the atria, right? We're suddenly having higher pressure in the ventricles and low pressure in the atria. So blood wants to move back into the atria, but it can't because these valves are closed. And so that sort of sloshing back is causing a turbulent flow sound, this kind of wave sound. The motion of that blood kind of sloshing back, it is part of what closes those valves. The second sound is happening for similar reasons, right? It's still turbulent flow. This is a louder dub sort of sound. The semilunar valves close simultaneously. And then our ventricles are relaxing. So there is a backshift of blow from the arteries back towards the heart. This motion causes the semilunar valves to close, and then that blood that was flowing backward kind of sloshes around before it can reverse direction and go in the correct direction. So that kind of sloshing, that turbulent flow is what we're hearing. So we can see that that's happening here during these phases of isovolumetric contraction and relaxation. That's where we have some sloshing of the blood as we're changing the pressure in the ventricles. And that blood is trying to flow somewhere else. It's trying to flow backwards, it's trying to flow inwards, but it can't do it because the valves are closed. Okay, so I think I have to share my computer sound for us to be able to listen to some sounds. I like listening to sounds, so we're going to do that. So first we're going to listen to a healthy heart. So I want you to hear the lub from the first heart sounds, so from the AV valves, the turbulent flow as the AV valves close. Then I want you to hear the dub as the semilunar valves are closing and the turbulent flow is flowing against them. All right, so you can hear the lub dub from the AV valve, the turbulent flow to the AV valve, and then the turbulent flow to the semilunar valves. That once more. So this is probably a somewhat familiar sound. I think you've probably heard the sound of a heartbeat before. So hearing the sound tells us that those valves are shutting in a specific time, that we have blood flowing in a specific direction. We have it flowing there for a specific length of time. So some conditions can be found, diagnosed by listening to heart sounds. So sometimes we're going to hear heart sounds that are not normal. So we'll hear potentially turbulent flow where it shouldn't be, right? You can hear sloshing, moving for a longer time, moving back into areas where it shouldn't. Sometimes we will hear clicks from the valves, which we shouldn't hear. We shouldn't hear the sound of the valves themselves, but in some conditions we will. So I'm going to play for you the sound of aortic stenosis. So aortic stenosis is when we have basically kind of calcifying semilunar cusps in those aortic valve, in the aortic valve. So we'll hear that sounds different when we're not able to appropriately open and close that semilunar aortic valve. So this heartbeat, I believe, is a little faster, but you'll hear that you don't hear that lub-dub sound, right? Instead of hearing a distinct dub sound, you hear kind of a crescendo and then decrescendo, right? So you hear something kind of sloshing, going louder and then softer. So this is because we have a problem with those aortic valves. So the flow, that turbulent flow through them, is first getting constricted. It's getting, yeah, we can tell that the blood is not flowing correctly because we don't hear that characteristic sound. So I'm going to just play it for us once more there, a little louder. So when we say we can hear a heart murmur, this is the kind of thing we're talking about. We can hear the flow of blood. We can hear that it's not doing what it should be doing.
So in the aortic stenosis one, and are the valves closing? Because I know you kind of just explained it, but if you could explain it again, that'd be great. Because it kind of just sounds like one sound. Like I don't really hear I don't know, the two different sounds.
Yeah. And I will confess, I'm not an expert in heart sounds, but yeah, what's happening is that those valves, they're kind of like crunchy almost, right? So they have trouble opening. So that's one of the things you're hearing, is that the blood flow isn't going smoothly. So you're hearing turbulence during that push out. So during the ejection, you're hearing, and you're also kind of hearing during the next phase as well, relaxation, you're kind of hearing a swoosh as well, because they may not be opening or closing fully. So that's why they're kind of blending together, right? So here we can hear the blood being kind of constricted as it should be flowing out the aorta. So we hear some turbulence because they're not really totally opening. So that's why we almost don't hear the lub, because we hear this kind of swoosh happening during this phase. So that's what's causing the blending here. And then the dub is also kind of more of a decrescendo because they're also not totally closing correctly. Does that kind of make sense?
That makes sense. Because I couldn't hear two sounds. It kind of just sounded like one.
Yeah. Yeah, and you're not wrong. They do kind of sound like one, because we're having this crescendo and decrescendo where we shouldn't.
Okay, thank you.
Sorry, just turning off my computer sound. So I get little alarms when people enter, or exit, or message me. So. Ah. Okay. So we want to think back. So you can go ahead and flip back to that diagram of our pressure volume curve. Okay. And I want you to think about what it would mean if we saw a right shift in the end systolic volume. So a right shift. So I'm gonna actually scroll back just so you know what I mean? So say we're seeing a right shift. So like we're moving to the right. So this was kind of a difficult question because we haven't talked, I don't think we've talked much in the slides about the difference between compliance and contractility. So the difference between compliance and contractility is compliance is basically like kind of how hard it is to push volume into something. So like when I blow up this balloon, right? You know that there's elasticity in the walls storing the pressure, but how hard I had to push in order to put this volume of air in there, that's what compliance is. So you can think about like this balloon, like a water balloon compared to one of those foil balloons, right, that you might see for a birthday or like, I don't know, at a florist or something. Those are much easier to blow up. They're not very elastic, but you can put in a bunch of volume without having to expend a bunch of pressure. So it does cause greater filling. I think these little explanations at the end are tripping people up a little bit. It does cause greater filling, but it wouldn't cause an increase in end systolic volume in total, because at the end of systole, that's after we've contracted. So it's after we've pushed blood out. So if we see a right shift, so increased volume at the very end of systole, this actually means that we have less contractility in the heart. So we might have had greater filling, right? That would overall give us more volume, but specifically we'd see the greater volume at the end of diastole. So if we had a bunch of compliance, if we had greater filling, that's when we would see a lot of volume. If we still have a bunch of blood in the ventricles at the end of systole, that means we haven't been able to contract the heart muscle enough to squeeze it all out. So the answer here would be D. I think this is our final poll question. Okay, so we want to remember what our mean arterial pressure is. Okay, I'm going to go ahead and end our polling on this one. Okay, so little bit unsure about whether we're talking about all the arteries or just the aorta. We do measure mean arterial pressure at the aorta, so it would be the average aortic pressure during the cardiac cycle. We're interested in the pressure at the aorta specifically because that's what's sending the blood out to our systemic circuit. Okay. Actually, we do have one more question just about this relationship between stroke volume, pressure, contractility, heart rate. So what would not increase the stroke volume? So which of these would not increase the amount of blood that the heart expels during a single heartbeat? Okay, I'm going to end polling just so we can go over the answer real quick before I close up for today. So the correct answer, what would not increase stroke volume, is D, the increased heart rate. The reason for that is stroke volume is telling us about the blood that's being expelled during a single heartbeat. So increasing the heart rate is not going to be changing the stroke volume per se. It might be related to other changes. And we'll see as we talk about sympathetics and parasympathetics, how heart rate does go along with some other effects in the heart. But increasing the heart rate by itself doesn't increase the stroke volume. But we would see that these other things do. So if you have more blood in the heart, so if you increase the end diastolic volume, if you increase the amount of blood in the ventricles when they're full, then when you squeeze on them, you're going to be increasing the amount of blood expelled from the heart. So increased end diastolic volume would increase the stroke volume because there's more blood to squeeze out. Similarly, increased contractility. If you contract the heart more, you can send out more blood. We saw that at rest, we're only getting rid of like 54% of the blood in the heart. So our ejection fraction was only 54%. If we increase contractility, we could increase that number. And finally, decreased arterial pressure. So if we have a decrease in the pressure in the arteries, blood likes to go from high pressure to low pressure. So if we decrease the arterial pressure, we're going to end up increasing stroke volume because more blood is going to want to flow to that low pressure region. Okay, so that's it for today. And our last topic is going to be cardiac output. So we'll go over that on Monday. And that will be it for this class. You do have a quiz that's up. So that's on what we've done this week, which I believe is electrical signaling and some of this cardiac output stuff. Yeah, so it's whatever we did this week. But I think it's mainly those two things.
Any quick questions?